So for the next session, we have a set of talks about quantum chemistry, kind of quantum simulation, put them together. So first we have Martin Head Gordon from Berkeley to tell us about quantum chemistry.
Okay, thank you, James, and thank you, Andrew, for the invitation to come here. I've been enjoying the morning and learning a lot here, and I hope I can pass on a little of what I know to you guys and maybe entertain you a bit in the process. So, well, quantum chemistry is the branch of chemistry that's concerned with trying to predict the fate of chemical reactions using quantum mechanics. And what I'll tell you about today is a sort of a general overview, and then a section on density functional theory, which is the most widely used quantum chemical simulation method, and then wave function theory. And I'll divide the talk roughly into equal halves after the introduction. Okay, so let's go back to 1830 and amuse you a tiny bit with Auguste Comte was a natural philosopher, and he said that every attempt to employ mathematical methods in the study of chemical questions must be considered profoundly irrational and contrary to the spirit of chemistry. And he went on that too much mathematics would lead to a rapid and widespread degeneration of the subject. So it appears we live in degenerate times. Anyway, so 1830, nearly a little over 100 years later, G.N. Lewis built up the College of Chemistry at UC Berkeley. He's one of the giants in whose footsteps we follow. And in volume 1 of the Journal of Chemical Physics, which is perhaps my favorite journal, he wrote, "In the Schrödinger equation, we very nearly have the mathematical foundation for the solution of the whole problem of atomic and molecular structure." This was a big concession coming from this guy, because only about a decade or so earlier, he had developed the qualitative electron pair theory of chemical bonding. And here he was admitting that this really needed to be superseded. But then he said, we require a great further development of mathematical techniques. So anyway, so my job is to try and tell you a bit about how chemists have coped with the necessity for a great further development in mathematical technique. And we are trying to solve the Schrödinger equation in the clamped nucleus approximation. So this is a nasty-looking eigenvalue problem, partial differential equation in the coordinates of the electrons. The nuclei are clamped, so they provide simply a fixed field. We have kinetic energy, electron-nuclear attraction, and electron-electron repulsion. The eigenvector, the wave function, needs to be an anti-symmetric function of the electron coordinates, because electrons are fermions. And this annoying Coulomb potential prevents us separating variables, alas. If only we could separate variables. So if we could separate variables, the eigenfunction would be a determinant. Since we can't, the eigenfunction must be a superposition of determinants and may in general be a very complicated one. The lowest eigenvalue, E0, will be the objective of my talk. One could worry about excited states as well, but with a half hour, let's simplify. And it is an implicit function of where the clamped nuclei are. And therefore, as the clamped nuclei are allowed to move around, the lowest eigenvalue defines the ground state potential energy surface, and that is the surface on which chemistry happens. Molecules correspond to local minima on the potential energy surface. They are separated, well, different molecular isomers are separated from each other by saddle points, which are reaction barriers, and chemical reactions connect one minimum to another. So if one can solve this equation, one can simulate chemistry, and over the past more than half century, chemists have become quite good at making approximations. Those approximations break down in certain limits, and there's opportunity to go beyond them, and that's a part of what people pursue in quantum computing for quantum chemistry, but nonetheless, the existing models have great value. And one piece of sort of model philosophy is important to highlight, because it's a contrast with what's often done in the physics community, and so it's important to be aware of it, that what we do is we solve the wrong equations very precisely. Okay, we are not looking for an imprecise right answer. We are looking for a very precise wrong answer. Why is this? Because we are connecting one local minimum to another. The energy differences are the significant thing. It's not the absolute energy. We don't care at all about the absolute energy. We care only about the energy differences. So we must solve the models precisely enough so that if we first weigh the Queen Mary and then we weigh the Queen Mary with her captain on board, we can get the difference. And one might say that's a silly way to do things, but we haven't been able to come up with a better one. Okay, so practical usage. Hundreds of thousands of chemists use electronic structure tools today, implemented in on the order of 10 or 20 large software packages. Some are commercial, some are public domain, some are kind of hybrids. I was a co-founder of one that's now embarrassingly a quarter of a century old. It consists of about 10 to the 7th lines of C++ code, has about 10 squared, roughly 100 pi contributors, and it's open teamware in the sense that we sell it, but pieces of it are public domain, and anyone can join our development team, and in some sense one needs a consortia to put together something that can do everything that a chemist wants to do. And so what does a chemist want to do? Well, the typical applications are trying to unravel chemical reactions that are not so simple that an experimentalist knows intuitively what's happening. So this is an example of a reaction path towards the green synthesis of the precursor PTA that goes into plastic bottles. And it's just showing you that there is an elaborate set of intermediates that correspond to local minima on potential energy surfaces, separated by various barriers. And so a student in my group worked on unraveling this reaction pathway. You can never prove a reaction pathway is right. You can only prove it's wrong. So this is a pathway consistent with the experimental information, and it's a typical application of electronic structure theory, which is many, many calculations performed, complex workflows using approximate solutions to the Schrödinger equation.
Is this problem also described by the Hamiltonian with the clamped nuclei?
Yes, absolutely. So this is approximate solutions to the Schrödinger equation with clamped nuclei. This is one particular clamping, another, and one can then walk on those potential surfaces, gradient following your way down to local minima, or with more difficulty going down in all but one direction and up in one to find a saddle point, a reaction barrier, which is something like this. And so this is just a snapshot of the kind of chemistry people want to do. This is actually a picture of our simulation cell. The atoms that are shown as balls and tubes are simulated quantum mechanically, and it's embedded in an electrostatic framework, because this happens to be catalysis in a zeolite. Almost all hydrocarbons are processed through a zeolite. But anyway, this is in some sense a representative example of what people do.
Problem still difficult with just a few clamped nuclei and many other particles, or?
Well, here we have on the order of around 30 to 40 clamped nuclei. So the potential energy surface that we're moving on is then roughly 100 dimensional. And so gradient search to walk on the potential. So step one is to solve the Schrödinger equation, get the eigenvalue as a function of position, the positions of the clamped nuclei. Step two is compute gradients and maybe curvatures on that potential energy surface, and then those tools can be deployed to search those surfaces and, with the aid of human intuition, uncover reaction mechanisms. So the complexity of doing that minimization rises as the number of atoms in the system increases. There's a combinatorial search problem eventually. But of course, chemists understand a lot about chemistry and therefore, in some sense, help avoid that combinatorial problem. Okay, so 95% of chemistry is done with density functional theory, so I need to tell you something about DFT. But the future, in many ways, belongs to the 5% of problems that can't be done with DFT. One of my software collaborators says, well, really, 95% of chemistry is easy. Well, and that means that density functional theory is really directed at the easy chemistry. Okay, so there are two branches to the quantum chemistry family tree, and one is modeling that exponentially complicated wave function. The other is modeling the, in principle exact, in practice unknowable density functional. And both of these define model chemistries, different approximations, different models, which are solved precisely enough that we can get those energy differences with the significance we need. And any approximation balances accuracy against feasibility. In other words, the perfectly accurate result, in principle, we know it, we know how to get it, but it's perfectly unfeasible, and the perfectly feasible ones are often perfectly inaccurate. Okay, so speaking of feasible and possibly inaccurate, we'll turn to DFT in a minute. Yeah?
I have a question concerning the picture before. So, how important is an experiment to this? Like if I give you a reaction and you do the calculations without looking at experimental data, can you get the right answer?
In principle, in practice, the way to see the progress of chemistry is kind of a triad between experiments, simulations, which are represented here, and then the abstract concepts of chemical reactivity. It's sort of a three legs of a table supporting the table of the chemistry. Yeah, so experiments are very, very important, in no danger of going away, especially because we're not always sure when our approximations become inaccurate. So in other words, validate, and also in a combinatorial search problem looking on a potential surface, we're guided by the fact that the chemistry happens. So we know there must be a low energy path through the potential surface to enable this catalysis to happen. It happens with a certain turnover frequency experimentally, and one can try to then aim to validate a candidate mechanism against that. Experiments are very, very important. Thanks for the question. Yeah?
How many nuclei? I mean, there must be a limit. Here you have 30 more or less.
Yeah.
I wanted to have 80, I'm sure
this is polynomial scaling. So in other words, so the cost is rising between the square and the cube of the system size if you neglect the problem of searching on the potential surface. So if the problem is just to compute the energy and the force and maybe the curvature, you can certainly do it for systems several times larger than this. And this is done on more or less mid-level computing, not a supercomputer. All right, so let's spend some minutes on DFT. I think most of you know this. I wasn't sure about the level here, but let's just say, why does DFT exist? So you can avoid the wave function. That's the wonderful statement of DFT. If you are after the ground state energy, you don't need the wave function. So the first Hohenberg-Kohn theorem says that an exact density functional exists. The energy can be written without approximation as a minimizer over all physically feasible densities, a function of the electron density and the external potential. That's the field of the clamp nuclei. And you can see this exists in terms of the electron density directly. The variational principle tells us a sort of in-principle answer to what does the functional look like. Well, you begin in wave function land as a minimizer over psi, though you really don't want to do that. And then you rearrange to first minimize over rho, and then minimize over the psi that give rise to a given rho. And this is the, in principle, exact functional, is defined by this very, very nasty looking mapping. So that tells us two things. First, a comforting theorem, you can do it. Second, we don't want the exact functional. We can't afford it. That would be worse than solving the full many-body problem. So actually what we want are things that are wrong, just not too wrong. Okay, so we are going to model a functional. We trade off accuracy against feasibility, and then in principle minimize over rho of r once we've made a model functional. Okay, so that was discovered some half a century ago in the mid-60s, and the sad news is that no one has yet succeeded in making a useful functional built in that general framework. So what should go into the model? The kinetic energy, the classical Coulomb repulsion, and exchange and correlation. And numerically, this is the biggest term, and it has been a consistent roadblock. No satisfactory kinetic energy functional exists. The search for one, if one could find one that is feasible, would be very nice. Yes?
Sorry, so there seem to be two challenges here. One is finding the energy as a function of rho, and then finding the rhos that are realizable by physical states. Is the second thing easy?
The second, neither of those are easy, and thank you for asking. So the first one is the functional design problem. The second is called the n-representability problem. Which rho of r's actually come from valid wave functions? Not obvious which rho of r's should actually be put in there. So So hence, a solution to both of these problems is Kohn-Sham density functional theory, which is really a beautiful sidestep. It's a retreat from pure density functional theory to use, in fact, the wave function associated with a set of non-interacting electrons. After all, then separability surely holds, and the non-interacting wave function is a single determinant. And furthermore, it solves the n-representability problem. If we use the non-interacting wave function to represent the density, well, then we make it out of the orbitals that describe the non-interacting electrons. So there's a fictitious system of non-interacting electrons that parameterizes rho and will then be used to evaluate the kinetic energy. We will now use the kinetic energy of the non-interacting electrons, hoping, and in fact, now believing on the basis of decades of experience that this is actually very close to the kinetic energy of the real interacting electrons. So now we have solved the problem of the kinetic energy. The next biggest, and we've got the classical electron-electron repulsion, we've just got to model the exchange correlation functional. That is what modern DFT is all about. And while a short talk is not enough time to do any justice to this, rungs on a metaphorical Jacob's ladder are used to classify approximate density functionals. There are several hundred widely used functionals these days, and the primordial ooze down the bottom here is where electrons don't even have the correct spin symmetry. And up here is the heaven of chemical accuracy, and by vague analogy with the biblical Jacob's ladder, we climb from the primordial ooze to the heaven, beginning with first the simple local density approximation, where the unknown exchange correlation functional just depends on the density at each point in space. Then we rise up another step to allow gradients of the density. So this would be exact for the uniform electron gas. That's a model system that solves that problem. You then assume transferability to create the functional. Here we are also exact for the slowly varying electron gas. And then we go up and we introduce second derivative information through the so-called kinetic energy density tau. And then we begin more or less hybridizing, that is increasing pieces of wave function theory into the density functional. So the first piece is a dependence on the occupied orbitals at rung 4. And then finally, in the kitchen sink spirit, a dependence on the unoccupied orbitals as well at rung 5. And that covers just about everything conceivable. So this category actually works in some sense. And here's a little bit of data for thermochemistry showing you rung 1, 2, 3, and 4. Diminishing RMS errors as a function of advancing up that rung for example functionals. And this game has been carried to a pretty high level of sophistication, and here's some sort of modern results, brand new ones really, summarizing tests of 200 different density functionals over about 5,000 trusted data points across roughly 7 or 8 classes of chemical energy differences, so no absolute energies, only differences. Non-covalent energies, this is the sticking of molecules together, both for dimers and for clusters. We distinguish those that DFT should get right as being easy, those that DFT might not get right by being difficult. So that's the D and the C. The D here, and then isomerization energies, that's rearranging a given structure to another one. Thermochemistry is breaking bonds, easy and difficult. And finally, the barrier from minima to saddle point is barrier heights here. And what you see is if you look at the best functional from rungs 1, 2, 3, 4, 5, you see a monotonic decrease with each step up Jacob's ladder as represented by the best functional at each level. And this top line, in some sense, is the best that can be done in 2018 to my knowledge. And so there's a root mean square error of slightly less than 1 kilocalorie per mole for barrier heights, slightly less than 1 for thermochemistry, more like 0.1 for non-covalent interactions, and if you don't like 1 sigma errors, multiply by your favorite multiplier to make them 2 or 3 sigma. And even for the difficult problems, where DFT is meant to have problems, it's also a monotonic decrease. So in a statistical sense, that is across 5,000 data points, DFT is systematically improvable by putting additional ingredients into the functional. Of course, that's only for the best functional at each level. The greater the freedom you have to design a functional, the greater the possibility you may design a bad one. And so the worst functional at each level actually begins to get worse as you climb upwards, because some people have made design mistakes. Anyway, that is in some sense my DFT perspective, and issues that could be addressed going forwards. One always wants higher accuracy. The accuracy I give there is just good enough for the kinds of applications that we typically want to do. Then maybe of more interest to this audience is the fact that DFT has well-recognized failure modes. It doesn't get everything right. There is so-called self-interaction error. That's the fact that, that electrons artificially interact with themselves where physically they don't. That's a defect of the exchange part of the functional. There have been historic difficulties now largely solved in getting long-range dispersion interactions. And then finally, of most relevance to you, I think, is the fact that DFT begins from a single configuration of electrons and therefore is almost guaranteed to break down in any problem, the so-called strong correlation problems, where many, well, more than one and potentially many determinants are involved. And there's an issue about design. At what point is one just playing a fitting game? That's a delicate question, because I play in that game. How many parameters are essential? Can you do it ab initio? Recent functionals have made progress on everything but strong correlation. And it's an open question, how much better can the density functionals 10 years from now be than the density functionals of today? But it's a safe bet they will be better. I think it's also a safe bet they won't solve this problem. Okay, so let's pause here. That's the end of the DFT part, and yeah.
The choice of which density functional to use for a particular problem, is it done ad hoc? Or? No,
it's not done ad hoc. I mean, well, it depends on what you mean by ad hoc. It's typically done with the
best one according to some other measure which is not defined by the DFT.
Yeah, it's typically done based on the experience of the user. So in other words, and it's often done with some initial validation on a problem that's a close cousin of the one you want to solve in order to check and see. As a developer of quantum chemistry software, I find that our users, our experimental users, view quantum chemistry codes as being like an instrument that might be miscalibrated. And so they usually trust but verify. Any other questions before I go on? Okay, so
H2 dissociation means that there was predicting that like H2 would not be stable?
This is a bit embarrassing. It's a one-electron problem, so there's actually no correlation present. But if you dissociate H2+, you get a potential curve that instead of looking like what it should look like, which is this, so this would be exact, the one-electron solution, you get something that looks roughly right out to about here, but as the bond stretches, collapses down here. So this would be, for instance, a GGA. So it predicts. The x-axis is energy. The y-axis is the distance between the. The x-axis is the distance between atoms. Y-atom is energy. This predicts that two H1 pluses are lower in energy than H and H+. So it would be a little like cold fusion. It's a potential source of energy, but it isn't. So that's this, and that's obviously an electron interacting with itself. So if you make two H1 pluses, that self-interaction is reduced. Alrighty, so now we'll switch gears and turn to the second branch of the family tree, wave function theory. And if the summary of DFT is low cost and moderate accuracy, the summary of wave function theory is systematically improvable at high cost. So it's a bit like applying a blunt hammer, sort of an instrument that's roughly right but not precisely right to solve the problem of your plumbing. Okay, and I'll tell you a bit about configuration, interaction, and coupled cluster methods, and I'll finish with a couple of remarks on strong correlation. So broadly speaking, we make two approximations in quantum chemistry. I've already kind of hinted at this. First, we solve the wrong equations. We don't solve the Schrödinger equation. We solve something close to it. So we typically make an electron correlation model, maybe starting with mean field, for instance, and then doing either CI or CC. And secondly, we don't work in the complete basis set limit for one particle expansions. We use a finite basis because computers far prefer finite dimensional matrices. So we typically use atom-centered functions with some maximum angular momentum on each atom, although one could use finite elements in principle, or plane waves are popular in condensed matter physics. And again, contrast with condensed matter physics is we always keep the full many-body Hamiltonian. There's a little asterisk here to remind me to tell you, well, that's in the non-relativistic universe. And the key virtue is systematic improvability, and in theory, it's the right answer for the right reason in this case, whereas in DFT, it's the right answer because we have attempted to cancel out systematic errors as best we can. Okay, so as a kind of a quick walk through a wave function hierarchy, you'd begin with mean field theory, which is, well, I really should have had a squared, a cubed cost. And it gets 99% of the absolute molecular energy, but I told you we don't care about that. And what's left over, the correlation energy, is 1 volt per pair of electrons. So if I take a chemical bond, for instance, between two hydrogen atoms, I pull it apart, I expose the full correlation energy of that chemical bond, or 1 volt, or 100 kilojoules per mole, or 25 kilocalories per mole. I make a giant error by neglecting the correlation. So even though I've got 99% of the absolute energy, that's useless for chemistry. You can apply perturbation theory, maybe get between 80 or 120% of the last 1%. That's no longer useful because DFT is more accurate. Or you can do coupled cluster theory, which treats the single and double promotions of electrons from the mean field into empty orbitals self-consistently. That gives you about 95% of the last 1% of the energy. Turns out that's still not quite good enough for chemical accuracy. You have to at least include the 3-body correlations. So CCSD parenthesis T or CCSDT gives you more than 99% of the last 1%. That is sometimes called the gold standard of quantum chemistry because it's about the most expensive thing you can afford, and it has finally typically gets chemical accuracy for problems that are not strongly correlated. All right, so to kind of jump back and look at the Hamiltonian matrix in the basis of the mean field reference, Hartree-Fock, single, double, triple substitutions. The mean field is optimized to 0 the off-diagonal coupling to singles. Because we have a 2-body Hamiltonian, there's 0 coupling to triples, so the leading correlation contribution are double substitutions. And therefore, that's why there's an obsession in quantum chemistry with double substitutions. What is a double substitution? Well, 2 electrons fluctuate transiently from occupied to empty levels, and the amplitude for doing so drops off very strongly with the overlap between the occupied and empty levels if they're expressed in real space. And also fairly quickly, algebraically, is r to the -3 with the distance between electron 1 and electron 2 also in real space. So the pair correlations are localized in a localized basis set. So configuration interaction is then to take a linear trial function, just as if you were solving the Schrödinger equation with reduced rank. And that, of course, is exponentially expensive to do exactly, so you truncate. And the simplest truncation would be to include single and double substitutions. That is variational. It treats multiple states on an equal footing, but fails to be what is called size consistent. In other words, you can't truncate CI and then get additive energies for non-interacting systems. So for instance, CISD is exact for 1 hydrogen molecule because there's only 2 electrons, so you only have singles and doubles. But if I do 2 non-interacting H2s, I won't get energy additivity unless I also include triple and quadruple substitutions. So this is really an unnatural form of the wave function to make truncations. So today, CI is very seldom used except for strong correlation, where you're typically not making a hard truncation. You're, in fact, either solving a small full CI or selecting configurations. So couple cluster theory is the preferred method to truncate with. And we can rewrite the linear wave function. Well, at first glance, it seems like we make the problem much worse by exponentiating the correlation amplitudes, T1 through Tn. But now truncation by substitution level is size consistent. And you can see that if I truncate at single and doubles, and I have the exponential here, I'm getting an accounting of triples and quadruples. So for instance, T2 squared is the interaction of the double on one system with the double on another system. That's where size consistency and therefore energy additivity comes from. So this is really a good thing to do and is what we do. How do we get the energy and the amplitudes? Well, we can't do it variationally because, in fact, the expansions don't terminate. So instead, it's done by subspace projection. You solve the Schrödinger equation in a subspace. For instance, the subspace of single and by closing the Schrödinger equation, projecting with single and double substitutions, and also projecting with the reference, you have sufficient equations for the amplitudes and the energy. So we now have closed nonlinear equations. Great. We have lost the variational upper bound in the process, so we can't assess the quality necessarily by that. And because we're solving in a subspace, the results will be best in the case where our projective subspace includes all of the important parts of the Hilbert space. So that will be the case where the single reference is kind of dominant. So in that sense, coupled cluster theory is aiming to solve similar problems to the ones DFT is aiming to solve, the ones where we're dominated by one configuration, or again, the 95% of chemistry that in some sense is easy, meeting this criterion. If you climb up the ladder, you get exactness for increasing numbers of electrons that may be arbitrarily entangled while maintaining size extensivity, consistency, and the cost is always polynomial, but the polynomial power is rising rather rapidly. And remembering that DFT is no worse than a cubed, this is already the square of DFT, and that's not good enough for chemical accuracy. So you've got to be a seventh or a eighth.
A being what again?
The number of atoms. So assuming that we keep a consistent description in terms of one particle basis for all atoms. All right then, so let's just see it in practice. This is a kind of a beautiful figure where as you walk across the x-axis, we're increasing the one particle basis set. So this is triple, quadruple, quintuple, and hextuple zeta. Don't worry about the acronyms. And as we climb up the y-axis, we're going from singles and doubles to singles, doubles, triples, to singles, doubles, triples, quadruples. And so if you start down the bottom, the error distribution represented, for instance, in gray or in red, depending on whether you basis set extrapolate, is so broad you can't even see it on this scale. And if you climb up, for instance, in a fixed basis, you eventually reveal basis set limitations here through the width of the error distribution and the shift. Or if you fix the basis set while not fixing the correlation treatment, you eventually see the coupled cluster singles and doubles limit, but do them together, and this is a brute force way of systematically approaching the right answer for the right reason. So that's the message here. Coupled cluster theory works and therefore is used. All right, so I'll finish with a few remarks about strong correlation. So what I've told you about so far are mostly the electron correlations in stable molecules as exemplified, or atoms exemplified by the helium atom. So we've been attempting to describe the fact that you don't find two electrons in helium on the same side of the nucleus. You typically find them on opposite sides. So this is a dynamical effect, that 1 volt per pair of electrons, which implies a small role for many, many configurations. You have to sweat the details to get the chemical accuracy, but we are dominated by the mean field reference plus small corrections. Now we want to contrast this with the situation in strongly correlated systems, where there's a major role for more than one. Might be 2, might be 100, might be 1,000, a whole bunch of configurations. And this, by contrast with this picture, it's a near degeneracy effect. The energies of two configurations roughly balance, are nearly degenerate. And if you have nearly degenerate configurations, they'll mix strongly in quantum mechanics. So this near degeneracy effect is essential to be qualitatively right. And so the picture here is just the toy example of stretching H2. It's a little bit of a toy example in many ways. It's The strongly correlated regime is where the bond is partly broken, that is, the electrons are still entangled, but not fully broken, at which point the electrons are independent. All right, so what do you do to define the essential correlations in conventional quantum chemistry? Well, there are a couple of things. You may try to select the significant configurations within full CI. This is a little bit breaking the chemical model philosophy that I mentioned, but nonetheless, if you want to approach the correct answer, selected CI is undergoing a renaissance, and Norm Tubman, who I see sitting back there, has been leading that renaissance at Berkeley, and you can chat to him about this in detail. Ali Alavi really begun this with his full CI quantum Monte Carlo method. And then, as well or instead, you may try to solve the full CI problem, not in the entire atomic orbital space, but in a reduced space of chemically relevant, or you might say chemically active orbitals. And those can be defined from first principles, the pairing active space, where there's one active orbital per electron, so the active orbitals are then half occupied by definition, or the valence active space, where there's one active orbital per valence atomic orbital. Or more open-endedly and more dangerously, you may try to choose the chemically important active orbitals, at which point you've lost the notion of a model chemistry and instead tried to make a custom solution. Then go solve the Schrödinger equation in the active space. And if you can do that while optimizing the orbitals at the same time, that's called the complete active space SCF method, or CAS-SCF, and that's conceptually and practically important, but it's not the right answer. You've got to finally correct for dynamic correlation in order to be accurate. Okay, so let me summarize and stop. So the virtues of wave function-based quantum chemistry, in contrast to DFT, is the systematic improvability for a given molecule instead of statistically, and hence the right answer for the right reason. The challenges, which are about the rate of convergence, the kind of excessively blunt instrument for the delicate job of treating an interesting molecular problem, and the high rate of increase in the cost of computation. There's lots of ongoing progress on both fronts that I don't have time to tell you about. What I really do want to emphasize is that strong electron correlation is an unsolved challenge, because regardless of the progress, exponential scaling challenge basically remains, and there's much ongoing effort within the quantum chemistry community to seek novel approximations, some of which are inherently polynomial, but it's not clear they're accurate enough to be generally useful. So anyway, I'd like to stop there, and thank you very much for your attention.
One of the things that, of course, interests all of us is dynamics. So how does the situation look here from the point of view of both DFT and coupled cluster?
So when you say dynamics, do you mean dynamics of the nuclei or dynamics of the electrons?
Both.
Both. Okay, well...
Simplest case, of course, electrons with the nuclei. But usually what happens is that when I start doing too much with electrons, the nuclei will start...
So we would normally say dynamics of the nuclei is a sort of a separate issue. In other words, once you've solved the potential energy surface, you either walk on it or you propagate classical or perhaps semi-classical or even quantum dynamics on it. It's a separate issue. So in other words, this is then the kind of prerequisite essentially to doing nuclear dynamics. On the other hand, I did restrict myself to solving for an eigenstate here. So if your interest is in electron dynamics and things like strong field phenomena, then there's a relatively small sub-branch of quantum chemistry that is concerned with solving the time-dependent Schrödinger equation for many electron systems that are not in stationary states. And that would be appropriate for modeling strong field phenomena, for instance. So there's activity there, yeah.
Yeah, well, this is a quantum computing conference. So as far as I understand it, the quantum chemistry people who use quantum computers use many of these techniques, but they go to much bigger basis sets because they have access to them with the quantum computer. Are you optimistic about that as approach? Do you have any thoughts about it?
Well, I'm not the best person to prognosticate on that, but what I would say is that that competing against established quantum chemistry on its home ground of problems that are dominated by a single configuration is pretty tough. But there is a big opportunity for trying to do a better job on strongly correlated problems. So getting to the basis set limit in quantum chemistry, the one particle basis set limit, is a problem that we have a reasonable handle on. Getting to the many electron basis set limit, that is the correlation problem, is only adequately solved at the moment for problems where strong correlations are relatively low rank.
So I had one question. You talked about this complete active space for substitution methods. What about for a couple cluster? Is there something similar for active spaces?
Yeah, so one could say, well, you could then try and make couple cluster approximations to the wave function in the active space. So for instance, that has been tried, and it's useful if the level of entanglement is not too high, and if the entanglements in the active space are essentially full rank, you might as well do configuration interaction, because then you have to go all the way up.
I'm trying to see if I understood your previous answer. So your most precise method scaled to n to the 12, right?
Yes.
And you said that a quantum computer would have trouble matching the accuracy or the results given you by the classical method?
Well, maybe very few people use the a to the 12th scaling methods in practice. So really the relevant comparison is against the a to the 7th scaling methods. Those are the thing that I mentioned as the gold standard. That is feasible for systems up to perhaps some 15 or 20 atoms, and is quite widely used, but density functional theory is the thing which is predominantly used. So quantum computing has the chance to perhaps attain greater precision, surpass couple cluster theory, but I think the bigger opportunity is where couple cluster theory breaks down.
Maybe we have time for one more question.
Your choice is the main problem to determine pathways, as you mentioned before, or there are other things that are more important than
Well, for chemical reaction modeling, you first pick a model chemistry, so that's what I've concentrated on in this talk, surveying the model chemistries. Then you have to adequately search the potential energy surface using a mix of human intuition, so-called chemical intuition, and appropriate algorithms for maybe automated saddle point searching and so forth.
If you got
Okay, one last one.
Okay, real quick. For the non-chemists in the audience, what specifically are the right problems for them to look at for finding an advantage for a quantum computer, i.e. where do you see are the most important places to look for an exponential advantage for an FCI solution practically?
So typically it's the antiferromagnetic coupling of different transition metals. There's a variety of examples of such systems that are well known. So one example is sort of ferredoxins, which have iron-sulfur clusters, and on a given iron atom there are either 3 or 4 unpaired spins, but the entire system spin recouples to be low spin in the ground state with a whole bunch of low-lying excited states. That's an example. There are many others.
Right. Let's thank